Good afternoon, everyone. I am Alice Lucchetti from the Astronomical Observatory of Padova, and I'm going to give you this seminar about the JUICE mission that is en route to the Jupiter system. So my idea is to give you an overview of such a wonderful mission that will characterize the Jupiter planet and its icy satellites. And in particular, I would like to give you this overview of the mission, along with an overview of one of the instruments that is on board JUICE, that is the Janus visible camera. So, firstly, it is important to understand which are the science objectives of JUICE. There are two different science objectives that are the major objective of the mission, and it is an emergence of habitable worlds around the gas giants because we would like to characterize Ganymede as a planetary object and possible habitat, Europa, recently active zone, and Callisto as a remnant of the early Jovian system. These are the three icy satellites of Jupiter, and we would like to try to give additional information and try to solve and to reveal the secrets about such bodies. Then the second science objective is the Jupiter system as an archetype for gas giants. And in this context, we would like to investigate both Jovian atmosphere and magnetosphere, but also to try to analyze the Jovian satellites and the ring system, because as you know, there are different irregular satellites that are around Jupiter, and the Jupiter has also ring that are not spectacular like the one that we can see on Saturn, but also the ring system is very important also for this planet. But the first question is why we chose Jupiter icy moons? Because, for instance, Europa may vent water vapor to space via plumes and geyser, and Europa is a body that is very important from an astrobiological perspective. It is very young and active. It is a geological active body, and it is very young, and we know it because there are very few impact craters, but this satellite is characterized and covered everywhere by fractures. And JUICE will fly by 2 times Europa, and the JUICE closest approach will be at 400 kilometers. And the JUICE main goals of regarding Europa will be searching for biosignature and pockets of water, exploring geology, surface, subsurface activity, and also the environment around this satellite. Then the second topic is Callisto, as I said before. Callisto is a body that is very particular because it is very old with respect to Ganymede and to Europa. It is covered by craters, impact crater, and so it is a window on the early Jovian system, in the early also solar system evolution. There will be a 21 flyby of Callisto, and the closest approach to Callisto will be at 200 kilometers, but I will show you later what I mean with the flyby and also with the number and the closest approach distances. The main goal of the JUICE mission will be to characterize the environment around Callisto and understand the origin of a mysterious magnetic field. Then there is Ganymede. Ganymede, it's the largest satellite in the solar system. It is very peculiar because it has its own magnetic field, and it's characterized by two different units that are the young terrain, that are the groove terrain, the light terrain, and the dark terrain that are older one, and that are mainly characterized by impact crater, while the light terrain are characterized by the presence of tectonic features that are called the grooves. But maybe you have already seen such feature with the Costanza and with the exercise that you did. And Ganymede objectives are exploring its magnetic field, its hidden ocean, characterize the ice content, the shell, the interaction with the Jupiter past and present activity, and also try to investigate the habitability of such satellite. There will be 12 flyby of JUICE regarding Ganymede, but the most important thing is that JUICE will be the first mission. It is a European mission that will orbit around an icy satellite, and that will be Ganymede. The other science objective are the characterization of the complex environment of Jupiter. In particular, we would like to characterize the atmosphere, as I said before, because there are such many mysteries that remain unsolved despite the Juno mission. Then we would like also to characterize the magnetic environment because there are auroras on Jupiter, and it is also important to understand the correlation and the interaction between the magnetic field of Jupiter and the magnetic field that are induced on the icy satellites, and also the particles that are surrounding the high energetic particles that are surrounding such a planet. Then another topic will be Io. We know that Io is a volcanic body. It is the Luna Park of volcanologists, and we would like to define what is the volcanic activity on the most active body in the solar system. We would like to determine where and how intense is the volcanic activity and how is shaping Jupiter's plasma environment, and also characterize the relationship between Io and the other icy satellites. And as I said before, there is also a very peculiar and fascinating environment of dusty rings and smaller moons around Jupiter, and we would like also to characterize such features. But focusing on JUICE, this is the spacecraft. JUICE is a mission, as I said before. The dry mass of JUICE is 2,420 kilos, and the propellant tank capabilities is 3,650 kilos. The instruments weight is 280 kilos, and we have a solar array that are very big because they cover an area of 85 square meter. Obviously, on JUICE, there are different instruments. There are 10 science instruments, plus one experiment, and plus one radiation monitor. In particular, the onboard instruments can be divided in three different categories that are the remote sensing instruments, as you can see here. And the remote sensing instruments are the optical camera system that is called JANUS. Then there is the visible and infrared imaging spectrometer that could give us information about the composition of the icy satellites and also of Jupiter, and it's called MAGIS. Then there is the UV imaging spectrograph, UVS. It is very important because if we would like to observe aurora, for instance, we can observe it with the UV. And then there is also a sub-millimeter wave instrument, SWI, that could give us information about the temperature that we could have on such bodies. Then there are the so-called geophysical instruments because they are characterizing the internal characteristics, interior of such satellites. And there is the radar sounder, RIME, that is very important because it can give us information about the interior till 9 kilometers below the surface of the icy satellites. Then there is the laser altimeter that is called the GALA, and it is very important because with GALA we can also try to understand the elevation of the surface that we are observing. And then there is also 3GM, the radio science experiment, that could give us information about the gravity environment of what we are observing. Then there are the in situ instruments, and there is the magnetometer whose objective is to characterize the magnetosphere, and so also the interaction between the magnetic field of Jupiter with the magnetic field of the icy satellites. Then there is the particle environment package that is called PEP, and the radio and plasma wave instruments. Then there is also the Doppler experiment, it is called PRIDE, that is mounted on board JUICE, and we also carry a radiation monitor that is another instrument that is on board the spacecraft. So as you can see, there is a variety of instruments, and it is very important because we are arriving at the Jupiter system, and at the Jupiter there are different topics that you can study because you can be the environment scientist, but you can also study the surface of what you are observing, the composition, and so to understand and try to reveal the secrets about the Jupiter system itself, we need a lot of different instruments on board the mission. But let's move to the launch and deployment timeline of such a mission. JUICE has been launched on the 14th of April of 2023, and JUICE was placed on Ariane 5 7 days before the launch. Then there was the encapsuling, the fairing, and one day before rolls out to launch to launch pad. Then there was the launch, and then the sequence after the launch was the spacecraft separation. Then ESA starts tracking JUICE, then there was the solar arrays deployment, and then deployment of antennas, probes, and magnetometer boom. JUICE arrives in French Guiana in February 2023, and there was the launch preparation campaign at Spaceport between February and April, and then there was the launch on Ariane 5 on 14th of April 2023. So last year there was this spectacular launch of JUICE. The main events of such a mission before arriving at the Jupiter system will be the next lunar Earth flyby this August this year. Then there will be the Venus flyby next August of the next year. And then there will be two different Earth flyby in September 2026 and January 2029. And then we will arrive at Jupiter in July 2031. So there will be a very long journey to Jupiter, but we are very excited about that. And then there will be 35 icy moon flybys between July 2031 to November 2034. And at the end, we arrive at Ganymede in December 2034. And then we will be in orbit around Ganymede. And as I said before, this is the first time that a mission will be in orbit around an icy satellite. Here you can see a movie that is showing you the launch and then also the first orbit around the sun. That will be between April last year and August this year. Then there will be the Lunar Earth Gravity Assist that is happening this year in August, and it is the first time that the mission is doing this type of flyby. Then there is the second orbit around the sun, between August 2024 and August 2025, the Venus Gravity Assist, the flyby in August 2025, and obviously during this flyby, all instruments are active and will acquire data. Then there will be the third orbit around the sun between August 2025 and September 2026, the first flyby with our planet. Then there will be the fourth orbit around the sun till January 2029. And then there will be the second flyby with our planet, as you can see here. And then it is very important because the next phase after this flyby with our planet will be the Jupiter orbit insertion, as you can see here, because we have the phase of transferring the JUICE mission to Jupiter, the JUICE spacecraft to Jupiter, and the insertion in orbit will be in July 2031. We will arrive at Jupiter. There are the first flyby of Ganymede in July 2031, and it is the first of 12 flyby of Ganymede. And then there is the Jupiter orbit insertion first orbits in the second half of 2031, as you can see here. So as you can see, the spacecraft is within the Jupiter system. Then there is the orbital energy reduction phase because we have to decelerate our spacecraft, and in order to have a different inclination and try to study also different topic of the satellites that we are observing. And as you can see here, this is this type of trajectory. Then there will be 2 Europa flybys in July 2032 in 15 days. And these are very important because are the only 2 flybys of the mission around Europa. And then there will be the Callisto flyby. And for instance, here you can see the second Callisto flyby. It is the second of 21 Callisto flybys. It's very important because with this flyby, we can cover mostly the surface, not the overall surface, but a very large part of the surface of Callisto. Then there is the high inclination phase, because we have to move and to change our inclination, the inclination of the spacecraft, in order to moving to the low orbital energy phase from July 2032 to December 2034, before inserting in orbit around Ganymede, and this will happen in December 2034. And here there will be an elliptical orbit around Ganymede at the beginning. Then there will be a circular orbit around Ganymede at 500 kilometers. And this means that we can also observe the surface of such a satellite with a resolution of 75 meter per pixel. And then there will be also another circular orbit around Ganymede. Here you can see the 500 kilometer altitude orbit around Ganymede, as I said before. And these give us the possibility to cover the entire surface of the satellite. And then there will be maybe another reduction phase that lower the altitude of the circular orbit at 200 kilometers before impacting into Ganymede at the end of 2035. Okay, but which were the major challenges and which are the major challenges of such mission? The first one is that there is a high dose of radiation within the Jupiter system. And so the solution that engineers found was to use shields to protect sensitive electronics. Then another point is the low power, because we are very far from the sun, and the sunlight is 25 times weaker than the one on our planets. And so the solar panels with an area of 85 square meter to collect lots of lights. So there are very, very big solar panels. Then another topic was the harsh temperature, because we have very high temperature during the Venus flyby, but very low temperature when we will be at Jupiter. And so we use the MLI, the multi-layer insulation, to keep the internal temperature stable. And the other point was the antenna, because we are very distant from the Earth, and the solution was to use a 2.4 meter antenna to send data back home, and a powerful onboard computer that solves some problems independently. Here you can see some images of the Jupiter journey before the launch. Here you can see JUICE in this large space simulator before starting the thermal test on the left side, while on the right side you can see the integration and deployment of solar arrays. Then you can see here the packaging of JUICE for the transportation to French Guiana. And here, when the JUICE arrived at spaceport in French Guiana, there was the unpacking of the overall spacecraft, as you can see here. Then the Ariane 5 takes shapes ahead of JUICE launch, as you can see. And then there was the phase of moving the JUICE to the fueling facility in order to refill with fuel the spacecraft. And then the connection of JUICE with Ariane 5, because it was ready to connect it. Here are other images. You can see people that are fueling the spacecraft for launch. And here it is the Ariane 5 rocket for the JUICE launch that was transferred to the final assembly. Here it is the launch site, and here it was the day when JUICE was launched on the 14th of April at 1414 chest. And it was a spectacular launch, very very important. And here there are the first images of JUICE, the JUICE selfie that are saying goodbye to Earth. Then, as I said before, this is the journey of JUICE, but I would like also to give you an overview about Janus. It is one of the instruments that is on board JUICE. Janus is the high-resolution multispectral imager for the JUICE mission. It is a high-resolution camera selected by ESA through an international open call in February 2013, and it is the result of cooperation between different countries, Spain, Germany, England, Then there was also some other quiz from Italy, Spain, UK, USA, France, Japan, and Israel. So there are many, many different institutions that contributed to the development of these instruments. And we would like to thank of all these people because now Janus is on JUICE and is on its journey to the Jupiter system. But what is Janus? Janus instrument is made of 3 units. It is the optical aid unit, the proximity, and the main electronics. These are the main characteristics of a camera because it's very important to define what is the resolution of a camera, because for a scientist it's very important to define at what resolution, spatial resolution, I can see things on the surface of a planet. In this case, thanks to the characteristics that you can see on the left, we can achieve a spatial resolution that is 75 meter per pixel at a distance of 500 kilometers. And we can see the surface not only in the panchromatic, so not only in one filter, but we have 13 filters mounted on a filter wheel of Janus. Here, there are many technical things because Janus 3 units, subunits, etc. Then it is a telescope, so the optical aid unit, as you can see here. And these are some images that were taken before the assembly of the entire instrument. This is the main electronic units that was integrated on the spacecraft, as you can see here, that was made by DLR, and the proximity electronic units. Here it is the filter wheel on which filters are mounted, and the filter wheel was developed by Spain. And here it is the CMOS detector that was delivered by Open University, so UK. Then you can see here images where you can see Janus that was mounted on JUICE, so it was on board JUICE. And as you can see here, you can see also it is near the Gala instrument that you can see here, and there is a Janus. But which are the science goals of Janus? The science goals of Janus are the characterization of Ganymede, Callisto, and Europa as planetary bodies, including their potential habitability, with special focus on Ganymede. Study the exosphere of the Galilean satellites with special emphasis on Io and Europa. Characterize and study the physical properties of other satellites of the Jupiter system, including Io, the irregular and the inner satellites. Perform a physical characterization of the ring system. Study and monitor the external layer of Jupiter atmosphere, study the magnetosphere in which Jupiter and its satellites are embedded, and the complex interaction with the Jovian satellite surface. And in particular, the science objectives are those defined by a camera, because you have to take in mind that with the Janus instrument, we will have images, we take photographs of the surface of the planet. And so we can study different geological processes, geological features that we can see on the icy satellites. And for instance, one of the main characteristics of such bodies is tectonism, because we know that there are different deformation feature and associated strain. And so we would like to study such feature in order to provide a chronological sequence of it. Then we would like also to define the stress fields that cause deformation and stress sources, the lithosphere thickness, and also the exchange between the subsurface ocean and the surface by tectonic processes. Here you can see some example of Ganymede, different images that were taken by previous space mission, in particular by the Galileo spacecraft, the NASA Galileo spacecraft. But as I was saying before, on Ganymede, for instance, we cover the entire surface of the satellite with a resolution of 75 meter per pixel. Another topic that Janus we will study is the cryovolcanism, because we would like to study the distribution, the nature, and the composition of possible cryovolcanic feature. Then we would like also to define the range of eruption style and the relationship to the icy crust thickness and the impact of cryovolcanism on resurfacing. And here you can see some example of cryovolcanism on Europa on the right and on Ganymede on the left. Another topic is the habitability, because we know that both the tectonic and the cryovolcanic interaction between the crust and the subsurface ocean is directly linked with the habitability of these satellites, and it is a very important topic that needs to be addressed with such a mission. Then there are impact craters. Impact craters are very important because investigating such feature can give us information about the geological properties of the surface, regional differences of these properties, subsurface structure, nature of impactors, if were asteroids or comets that were impacting the surface of such bodies, and also determine a time-dependent morphological expression of specific properties. Here you can see different examples. For instance, two example of Ganymede, the Melkart, that is a central dome crater, and it is very important because such type of impact structure are present on icy satellites, because the dome, for instance, that you can see here in Melkart, is due to the diaparism effect. So material that was brought to the surface, and in some cases could break the surface itself, while in some other cases could not break the surface, and so there is a dome that is formed. On the left side, you can see another example, the Encke Catena, that is a crater chain, and this is a typical example of a comet that split in the atmosphere and then hit the surface of such a body. While in the Callisto example, you can see the Valhalla Basin, that is a multi-ring basin, very, very big, and this is another type of structure that we can find on such icy satellite surfaces. Then another topic that will be covered will be the rotation and internal structure, because we would like to define the spin pole direction, the amplitude of the libration, the determination of the rate of satellites orbit changes, and also refine the shape of such satellites. And we can do it with the Janus camera. And also the color characteristics, because as I said before, Janus is a camera with 13 different filters, and so these allow us to determine the distribution of lithological surface unit, the origin of dark contaminants, and other features like this. Then there will be also the study of minor topic that are IO's volcanic thermal activity and time evolution, because there will be the possibility to observe also such a moon. Then determine also the characteristics of the exosphere, and also the rings and small satellites that are characterizing the Jupiter environment. And last but not least, there is also the study of the atmosphere, because with the images, we can define the dynamical processes, the cloud system. We can also investigate the stratospheric variation of the atmosphere, and also trying to study the auroral activity in the upper atmosphere of Jupiter. But when we can do such measurements, in particular for Europa, we will have two different flybys. So we will have two flybys at the closest approach distance at 400 kilometers, and this means that we could observe Europa with a resolution of 6 meters. And in this case, we can cover the satellites with a three-color mapping with different spatial resolution. We can also do stereo in order to have a shape and a 3D model of what we are observing, and also study the exosphere of Europa. Then there will be 21 Callisto flybys. Also in this case, it will be very important because there will be flybys with the closest approach distance of 200 kilometers. And so this means that the resolution of what we are observing is 3 meters. And also in this case, we can have a regional mapping, panchromatic imaging of the surface, imaging of the surface with different filters, and also local stereo. And then there will be Ganymede. We will have 12 Ganymede flybys, and the elliptical orbit at 5,000 kilometers, and the circular orbit at 5,000 kilometers and 500 kilometers. This means that we will have resolution at 500 kilometers of 7.5 meter. And this means that we could achieve a global mapping of the entire satellites in different colors and also in panchromatic, plus different stereo coverage that give us information about the topography of such satellite. While for the Janus science measurements of irregular satellites, Io and rings, we will have a lower resolution because we will be distant from this target, but we can have the possibility to observe, for instance, the volcanoes on Io and also the rings from both the monochromatic and the colors perspective. And the last will be Jupiter. Jupiter will acquire images of Jupiter regularly, covering the temporal variability of the atmosphere. We will cover regional images with a resolution of 11 kilometers per pixel, and we can also observe the limb observation at spatial resolution of 10-20 kilometers per pixel. And with this slide, I finish my seminar. If you have any question, please don't hesitate to contact me. And I thank you all for your attention. Bye.